Hello everyone, and thank you for watching this presentation for the IEEE Symposium on Computer and Informatics. My name is An Nguyen from University of Information Technology, Vietnam National University. Today I will present our paper, VulnBridge, a unified function-level benchmark for vulnerability detection and CWE classification. Let me start with the problem that motivates this work. Learning by vulnerability detection at the function level has reduced a large body of research, and almost all of it is built on a handful of public datasets: Deviance, Review, Pitfall, Rustful, Civil Physics, Navable, and Megaballs. It's a with built for a specific purpose, which is on independent in engineering choices. This creates four problems that compound each other. First, the label schema are heterogeneous. Some datasets only provide a binary vulnerable or not labeled, while others attack CWE identifier at varying granularity. So vulnerability detection and CWE classification are rarely supported under the same protocol. Second, there is severe loss imbalance. Vulnerable functions are typically only 3 to 9% of its corpus, and CWE label follow a strongly long-tail distribution. Third, the same functions are duplicate within an address. If this is not addressed before splitting, training example leak into the testset and display the measured performance. And four, every study uses its own split reprocessing and matrix. The consequence is that when a paper reports again, we often cannot tell whether it's come from better model design or simply from dataset artifacts. This feature makes the problem concrete. Here, we saw accuracy, recon, and macro F1 average over the encoder we evaluated on the raw pen mask. Look at the gap. On Big Bowl, model reached around 94% accuracy. We are silent, but the macro F1 tells a completely different story. Our most tracking example was on Big Bowl actually 94 power 4% accuracy, but only 1.6% macro F1. The model is essentially just predicting the majority non-vulnerability loss. Record often fall below 30%. So, high accuracy on the benchmark is largely an illustration created by loss imbalance. This is the evaluation problem for is designed to fix. Our paper made three contributions. First, we present VulnBridge itself, a unified function-level benchmark built from on 7 public datasets, together with its full construction pipeline and a dataset. Dataset is publicly available on Hosting. Second, we provide a series of 8 encoder pipelines spanning 3 model families: general purpose, cost-specific, and security-oriented. On evaluate on the one-fifth protocol for both tasks arose on benchmark variants. Third, we report on empirical study organized around 3 research questions. In the construction pipeline 5 stage. In stage 1, stroke matching, we engage on 7 datasets into a common record format. The function test, a primary label, a CWE label when available, and relevant information so every record can be traced back to its source. Stage 2, function level deduplication with remote identical and near identical functions that recur within an address. Critically, we do this before splitting, which reduce the chance that the same function appear in post-training and the test data. The leaking from I mentioned earlier. Test 3, label normalization. binary label are marked to one convention and CWE label to a share schema, where a CWE label is unresolved and are inconsistent with its logit from CWE training, but the function keeps its binary label, so no data is wasted. Step for the Turkey selection, we rank CWE type by frequency and derive for variant top 10, top 20, top 50, and 4, which give us a control trade-off between coverage and difficulty. And the step 5 features trade define IT 1010 list. Every variant was small vulnerability and zero verification under exactly the same protocol. So the result like after unification and deduplication, VulnBridge contain 744,000 and 650 functions, of which about 53,000 are vulnerable, spending around 333 times and nearly 7,750 CV. That makes it clearer from every individual in both scale and CWE coverage. This figure on right shows the CWE distribution on a log scale, and you can see it is strongly long tail. A few witness type dominate, and both types are rare. This long tail is exactly why we build the top K variants. The table shows the four modeling really variants. Notice starting first, restricting to real CWE, repellent the data. The vulnerable rate rise from the 3 to 9% of Russell to between 39 and 52%. Second, coverage role with K. Okay, top 10 cover about 60% of the hit CW mask. Top 20 cover almost 80% and 4 retain on 100. 74 remain last. For the empirical study, we benchmark a retrain encoder in 3 families: general purpose text encoder, per distributors, and property cost-specific encoder, corpus, wrap corpus, and costivity, and security-oriented encoder, property contrapus. This grouping lets us isolate the effects of cost retraining and of security-oriented retraining relative to plain text retraining. All encoders share analytical processing, optimization, stratify split, and evaluation cost. Only top K labels may change between variants. We report accuracy, resistance, recon, and macro F1. And we define the accuracy F1 gap, the accuracy minus macro F1 as a single indicator of imbalance induced over optimums. All numbers are computed on the here-out text list. Or research question 1, what the unification actually requires? We trained and evaluated the same encoder directly on 3 rare representative Russell, Divines, people, and neighbors, and on the VulnBridge top 20. On the raw imbalance tool, the accuracy F1 gap is enormous. On before, the gap ran to 91.8 to 92.8 points. A ROS encoder on level is between 74 to 84 points. That is more balanced, so its gap are smaller, around 9 to 20 points, but still recent. But on the VulnBridge top 20, the picture changed completely. The gap dropped to near zero for every single encoder. Red corpus, for example, reached 78.1% accuracy and 77.8% macro F1, a gap of just 0.3, which record in the 70 to 80% range. In the feature, you can see the accuracy and macro par coverage after unification, whereas this tire support for reservation 1, function level deduplication, level normalization, and 2K rebalancing together make the respective matrix actually informative about model quality. In reservation 2, look at what happened as we widen CWE coverage. For binary detection, performance is stable. Across all value of case, accuracy stay around 73 to 79% with macro F1 low to accuracy. So the binary task is no longer reward measuring last precision, realistically coverage. The CWE classification task, however, current is coverage role. For recovers CWE's macro from 59.9% at top 10 to 58.7% at top 20 and 46.2% at full. And most encoders follow the same trend. The delay is steepest in macro resistance and macro recon, which reflects the difficulty of the rare CWE type in long tail. One important neuron. At full coverage, the CWE type very often accuracy versus macro gap focus about 14 points because everyone has CWE carry the accuracy while red tail last score fully. Unification lost the binary gap, but it cannot by itself remove the long tail penalty on file classification. This is exactly why we report macro average metric and 2K variance together rather than one single full coverage number. Research question 3. How do the model family compare on a level playing field? Specific encoder perform best and red cuts, but the strongest overall. It had the highest CWE macro F1 at every K and competitive binary accuracy around 78 to 79%. Among the security-oriented model, contrast is competitive, while VulnBridge trail is family on both sides. Interestingly, VulnBridge general purpose model is an exception. It outperforms several cost-specific models on CWE classification. The resistance recon profile run for disordering wrap compass has the highest binary detection resistance from top 20 through full, but keeping recon about 72%. The most violent profile is our source for trials where phone alarm and Smith vulnerability are both correlated. This violent behavior makes thruster aware red compass the most attractive default. The fraud direction, ghost retraining, and thruster aware retraining in particular have why the benefits of security-oriented retraining is model dependent. Let's close with the practical takeaway. First, accuracy alone is a poor primary metric for vulnerability detection. Macro F1 and recon should always robustic alongside. Second, a reference configuration. We recommend red covers or contrast on VulnBridge top 20 with pollen near 80%. His CWE covers again trackable difficulty and practitioner can treat K as an operating point control. Smaller K for resistant learning trees layer K for broader coverage at the cost of tail last performance. Third, the limitation stated honestly reach the label noise from the original source C and C++ only in a single functioning run without variant estimate. So our number should be rigged as byline. VulnBridge is released with 3 physics splits, AutoK variants, and dataset, and future work will extend language coverage and model families. Thank you for your attention. The dataset is available on Hudson Pay at the link. And we welcome questions and feedback through the conference form or by email. Thank you.